Okay, I think we can get started. Thanks everyone for joining. We have some changes. One is that Daniel Riedron, who was supposed to be the chair, cannot make it to the session, so I will have to chair this session. You can ask questions during the talks. You can use the Q&A feature. And for the speakers, I will give you a warning 3 minutes. At 3 minutes, I will just unmute myself and tell you, like, you have 3 minutes left. So our first speaker today is Francesco Iraci. Francesco, you can go ahead and share your slides.
Okay. So, hi everyone. I am Francesco Iraci. I'm a PhD student at the University of Cagliari in Italy, and I'm an EPTA member. And today I'm going to talk to you about a project that I'm working on about recovering techniques for PTA that are used to recover the interstellar dispersion. And I want to just start with a brief introduction, okay, on the effects that a radio wave emitted by the pulsar may undergo through its propagation through the interstellar medium. There might be dispersion, scintillation, or scattering. Dispersion is a frequency-dependent, it causes a frequency-dependent delay. Scintillation is a multipath propagation of the radio wave that is frequency and time-dependent, and it creates variations in pulse brightness, while scattering is also a multipath propagation effect of the photons, but it induces exponential scattering tail in the pulse profile. So I'm only interested in dispersion because it's what my project is about. So I will just talk about dispersion during the rest of the talk. So to be a bit more specific, I said that it's a frequency-dependent process. And we can see the frequency dependence in the refractive index of the interstellar material, that is an interstellar medium that is between us, the observer, and the source, the pulsar. And this changes since the refractive index is not 1 because of the interstellar medium, the group velocity of the radio wave is changed. This causes a time delay with respect to a signal at infinite frequency, which is the one that I'm showing you here. With this difference between the time of arrival at for a wave with a certain group velocity and the one that propagates at speed of light. And in the end, the time delay is given by this formula here, where d is the dispersion constant, dm is the dispersion measure, and f squared is the observed frequency to the power of 2. The dispersion measure is the observable quantity that we are interested in. And it is basically the electron column density along the line of sight, and it's given by this simple integral. And if we want to just to compute the difference in time of arrival between pulses at different frequencies, we just have to compute this simple equation, so given the dispersion measure. So, as I said, the dispersion has an influence on the time of arrivals. And these are clearly the main point of pulsar timing array, because with pulsar timing, we aim to predict the time of arrival of each single pulse coming from the pulsar, starting from a model, which is given by the parameter file, in which we have a set of parameters. From the model, we are able to create a prediction for the time of arrivals of each pulse. And then there are the observation, of course, and we have to compare the observation with the model just by computing the residuals. And the idea is to minimize the residuals, and to do so, we do like an iterative process of fitting for this over the data for our parameters, and then improving our residuals until we are able to get to a minimum value of them. So if I want to show you what happens now, since we are interested in dispersion, to the residuals when the dispersion measure is not properly taken into account into the parameter file. So I will talk today about multi-frequency observations, because the dispersion is a frequency-dependent effect. So we must study it at multiple frequencies. And on the left-hand side, there is the case in which our model is perfect, which never happens, with the residuals that are all zero, as you can see. And here, when I said multi-frequency observation, because at each point that you see actually corresponds 10 overlapped points at different frequencies. But in this idealized case, they arrive all at the predicted time, so the residuals are 0. If I inject actually a different value of dm, what happens is what we see on the right-hand side. So the dm in our parameter file is not anymore the correct one. And what we see is that there is a spread in the time of arrival of each pulse of each observation, because we see that corresponding to different frequencies, that is here highlighted here from the color map, we have different residuals. So again, a wrong dm may cause a delay in the let's say residuals different from 0. Now here the shape that you can that you see also from this residual is due to the fact that the injection that I've done is of a time variable dm, so it's not a constant value of dm that is wrong, but is also varying in time, because here there is the MJD on the x-axis. So to account for the noise, for this kind of noise that we may have in our data, we model it using power spectrum. So we're using power law for the power spectrum of the noise. So in particular, power spectrum is fully determined by the amplitude and the spectral index gamma. And for the DM noise, we will have a specific amplitude and specific spectral index. But DM noise is not the only one that is modeled with the power law for the power spectrum. Also red noise, which is associated to intrinsic spin noise of the pulsar, has its own amplitude and spectral index for the power spectrum. And also the gravitational wave background may be modeled with with a certain amplitude and a specific spectral index, which is 4.3, nearly 4.3 in the case of circular supermassive black hole binaries. So if we want to compare the spectral index of DM and red noise with the one of GWB, we see that most of the time their spectral index is lower than 4.3. It may happen that the spectral index for red noise is higher, but most of the time they are lower. And this means that basically the power spectrum of the gravitational wave background is higher at lower frequencies. Since the spectral index is higher, it means that it decreases faster, and the other two power spectra are flatter. So at higher frequency, we are not really able to resolve really well the gravitational wave background if we don't model correctly, if we don't take into account correctly the contribution of DM and red noise. And this is just a table of the last EPTA paper, DR2. So given this context, my project, let's see what I'm actually doing. And I am comparing different methods that are available to estimate the DM variations, so the DM noise, because there are many algorithms for between the collaborations. And the plan is to run a set of simulations and analyzing the outputs of my simulation with the three different methods that I'm going to show you, and then compare the results. Just to see the simulation that I'm doing, I'm using LipsTempo software, in which I can simulate time of arrivals, basically in the same way that I've shown you some slides ago, starting from idealized residuals with 0 residuals. Each observation has 10 simultaneous TOAs in the frequency between 100 and 200 megahertz, so low frequency. And then I inject different noise components like white noise, red noise, and DM noise. So what you see here on the right is an example of the residuals that I may have from my simulations. And it's important that you see that the spreading frequency is shown by the color map. And the fact that there is this spread in frequency is associated to a specific value, wrong value of DM epoch by epoch. So what I am able to do with my simulation is to store the injected DM time series, of course. And as you can see, it corresponds to one value of DM per observation. And then I try to recover the DM time series with the available methods that I'm using, which are epoch-wise DM using the software Tempo2, DMGP using Enterprise, and the DMX using Bind. So here you see just an example of the recovery from each method. And what I'm actually going to compute is the difference between the recovery and injection. So the DM residuals, what I'm going to call DM residuals. In the following slides, I'm going to show you some results of my simulations, which are actually given not from one single realization, but multiple realization given a set of parameters that I'm showing you here. And I start with the simple case of injecting only white noise and DM noise in my residuals. And what you see here is, again, the DM residuals as a function of the time, MJD. Colors corresponds to different models that I've used, methods that I've used to recover the DM time series. Blue is epochwise, orange is DMGP, and green is DMX. And you see numerous, lots of points because here I've run 1,000 iterations for this set of parameters, which means that I have 1,000 of DM time series injected and 1,000 recovery per method. So here you see that the behavior of the what we would like to have from these DM residuals is that they are Gaussian distributed around 0, centered around 0 with a certain variance, and the lower the better. But for what we are finding up to now for all the three models, it seems that they are Gaussian distributed, so they are white, there is no structure, and they are working pretty good with this simple case of white noise and DM noise. Now, when we add also the red noise into the picture, things start to be a bit more complicated because we have here again the DM residuals with the injected parameters here and here. Epochwise DM is in blue, DMGP is in orange, but I have to say that for the case of the red noise injection, both DMGP and DMX must include also the modeling of the red noise in before producing the DM time series. So here you see that epochwise seems to work basically in the same way as before. It's more spread than DMGP, and but it's centered around 0, so we are kind of happy with that. DMGP has some high frequency fluctuations structures in the residuals, but nonetheless it's working pretty good because it's centered around 0, and most of the points are here around 0. It's what we would like to have. Now, since DM and red noise are two different processes, DM is a frequency-dependent one, red noise is not, it's totally achromatic. I would expect that if we don't model for the red noise, there shouldn't be any difference in the recovery for the DM time series, since again they are two different processes. But this is not happening in the sense that when I do not model for the red noise and I try to recover the DM time series for DMGP and DMX, what I see is the points that you see in red and green, and we can understand better what's happening here looking on the right panel, because here is the injected red noise. So this is the time series that I've injected for each iteration of the to account for the red noise, and you see that it's basically the point.
Francesco, 3 minutes.
Okay. Thanks. The red and green points are mimicking the structure present in the red noise, so they are definitely absorbing some power of the red noise. And this is kind of a problem because again we are trying to recover the DM time series, but but what's happening is that this recovery is absorbing some power from another process, which should not happen. But so this is the point where we are right now with our simulations. I have to say also that this is quite an extreme case because the amplitude for the red noise is quite high if you compare also to the values that are present in the table that I've shown you before. But nonetheless, it's relevant that we are seeing some absorption, and what we are going to do is we are going to vary the values for the noise parameters, in particular for the red noise parameters, to try to address when and how much noise red noise is absorbed. So we still have to do some more, let's say, statistics, some more cases to study to address better this problem. But yeah, that's the point where we arrived up to now with our simulations. So just to make a summary of what I just said, I'm simulating TOAs, injecting different type of noises, white noise, red noise, and DM, and running the analysis for the DM time series with 3 different methods. What we see from our simulation up to now is that there is absorption of red noise power from DMX and DNGP when not modeling for red noise. And yeah, what we are going to do in future is we will investigate the parameter space. That is what I've also just said. We will implement, this is still missing, the DMX when you model for the red noise. We expect that it will behave like DMGP when modeling for the red noise. And then the natural follow-up project after this is to also inject gravitational wave background into our time of arrivals to see if each method is able or not to absorb it, so to see what happens basically when we inject the gravitational wave background, if there is some absorption or corruption of the DM time series. And that's it. And thank you for listening.
Thank you, Francesco. Perfect on time. Do you have questions for Francesco? Please. There's one on the chat. Bense, would you like to unmute yourself and ask the question?
I can't see that.
Let's see if Bense wants to ask it live. Otherwise, I will read it. Okay, so the question is, what's the difference between DMX and epoch-wise DM?
So that's a good question. DMX DMX is actually the method mostly used by only used by NANOGrav. Epoch-wise DM is used mainly in the analysis of low frequency data, like LOFAR, up to now LOFAR and NANOFAR, as far as I know. And the difference, it may be subtle, but I'm not sure about it. But in the epoch-wise DM, the fit works as follows. So you have the team file with all the observations, and you split the team file for like each observation will have its own team file, and the fit or in the tempo to fit will be applied only on that team file with the parameter file that you have at the beginning. So it's just yeah, what I've just said. For DMX, DMX is a piecewise linear fit done using Pint in the NANOGrav collaboration. I actually don't know the details of how it works, because it's you know, some specific things in the script, in the code of DMX, but I'm quite sure that are 2 different approaches which give similar results. I don't know if this satisfies your answer, your question.
Any other questions for Francesco? I can ask a real quick. You said when you are simulating your DM time series, you have 10 simultaneous TOAs.
Yes.
Does the number 10 matter? I guess if you increase it, it helps. If you decrease it, it's worse, right?
Yes. Well, the higher the number of TOAs that of simultaneous TOAs at different frequency, the better you're able to describe the variation in DM, because you have this frequency dependent effect, and the higher the spreading frequency between the TOA, and the better you see it. But actually, this works better at lower frequencies, because if you do the same process at 1.4 gigahertz or more, the L band, you will not be able to have the same you know, resolution on the DM effect, because of this frequency dependence, and the lower the better the frequency.
Thank you. I think we need to move on to the next speaker. So our next speaker is Kuo Liu.
Thank you.
Hello, can you hear me?
Yes.
Right, let's go to full screen. Okay, can you see my screen?
Yeah, looks good. Thank you. Take it away.
Right, thank you. Thank you, Maria. I also like to thank the organizer for offering this slot to talk. So today I would just like to give you a brief status update on where we are and what is to be expected from the third IPTA data release. So this is a presentation done on behalf of the entire IPTA data combination working group. Let's go. Right, so I presume everyone knows what IPTA is, but just to make sure we're all on the same page. So IPTA stands for the International Pulsar Timing Array Collaboration. So this is the PTA collaboration, or rather the community of the globe. So at the moment, we have full formal regional PTA members, the EPTA from Europe, the NANOGrav from North America, the PPTA from Australia, and the MPTA from India and Japan. So on the IPTA level, we are also working on with emerging PTA entities such as the CPTA and South Africa PTA. So in PTA world, we are really interested in using like the largest radio telescope on Earth. We grab these telescopes, use them to observe pulsars, conduct high precision pulsar timing experiment, and use our pulsar dataset to search for ultra low frequency gravitational waves. So the basic concept of the PTA has already been touched upon by talks given by Sarah Wigland and Golem on Monday. So if you're interested in that details, please refer to that talks. So the PTA world in the past few years has been really loud. I hope you feel the same because this is a very exciting moment of the PTA. So we have several rounds of major result and data releases. For example, around the end of last month, we have coordinated release from 3 major PTAs. That includes the EPTA DR2, the PPTA DR3, and the NANOGrav 15 years dataset. And around sometime earlier last year, we have also the first data release from the MPTA. And around similar period of time, we also have the first data release from the Meerkat and the CPTA. So this is very exciting. There's a lot of high quality data floating around. So it's exactly the same time, exactly the right time that we grab all the data on the IPTA level to see what we can get. So if you're interested in the detail of the data releases, you can refer to Dion's talk on the EPTA, and Joe Spiegel's talk on the NANOGrav 15 years, and Marty Mills and Ryan Shannon's talk on the Meerkat. I heard this talk is been canceled, but still you can read the paper if you like. Okay, so before we enter the science, we would like to first introduce you the community behind the scene of the DR3. So who is actually doing the DR3? So the leading force of the IPTA DR3 is called IPTA Data Combination Working Group. So this is the data combination task force of the IPTA. So at the moment, we have over 100 setup members for the IPTA data combination working group. So that reflects the size of the entire collaboration. And so at the moment, we have 3 co-chairs for the working group, Deborah Good, who recently are moving from New York to Montana, me myself, based on the Max Planck Institute in Bonn, and Golem Shaklan, who is based on the Milan Bicocca University. So as the name says, the primary task of our working group is to basically combine the release data from all the individual regional PTAs and to produce and construct the what is called IPTA dataset. So in addition to combining data, we also will run what we call the single pulsar noise analysis. And this is basically just to understand the noise component of each individual pulsar, and such that to understand the entire IPTA gravitational wave detector noise budget. So on top of that, we're also working on with other IPTA colleagues to define the IPTA data format and standard, try to make sure the upcoming future IPTA data sharing in a more streamlined fashion. So in particular, for the IPTA DR3, we've already organized 2 working busy week events, and there's another one to come around the late of this year. So here you can see that we have a very cheerful start in New York last year, and now in the middle of this year, things are getting a lot serious. Okay, so the breakdown of the IPTA DR3 contributions. So we have in total like 5 dataset contributions. We have EPTA DR2, NANOGrav 15 years, PPTA DR3, NPTA DR1, and Meerkat DR1. So the primary contributors of the dataset are the 3 founding members of the IPTA that provides the longest time baseline and also what is the frequency coverage. So over here, I would like to highlight the specific value for the newcomers, the INPTA and the Meerkat. So, for example, the INPTA are, although they have really a short time span coverage, it's actually doing simultaneous dual frequency observation going down to 300 megahertz to 1.4 gigahertz. So this is a very valuable addition if you want to model the ISM noise, as Francesco just said. So the Meerkat data, on the other hand, you can see that actually providing largest number of pulsars. So this is because there are lots of potentially good pulsars that to be added to the PTA. However, they couldn't have been done because of sensitivity limited by the Parkes radio telescope, so they could not be timed precisely. And now with the high sensitivity provided by Meerkat, this is now becoming possible. Right, so in total, the IPTA DR3 will include 115 pulsars with 25 years of time span and really wide frequency coverage. So this is really going to be the biggest and most sensitive PTA dataset ever made. And yet, upon top of that, we still have some possible further additions from other telescopes. So here you can see the sky projection distributions of all the IPTA DR3 pulsars, and the size of each symbol represents the number of PTA coverage. So you can see that there are only really a handful of points with the largest size. That means they're all covered by the all of the PTAs. So this is another way of looking at the advantage of going to the IPTA. We really have the optimal sky locations of all these sources. So because we really are going to have the best data set of the PTA, so that means we really have to do some sophisticated work in terms of analyzing data to make sure we get the best of this. So we come up with our IPTA DR3 work plan. So the plan for the data combination and single pulsar analysis part of the work is that we are going to use 2 fully independent pipelines to do the analysis. And for the data combination and the timing analysis, we are going to use the Tempo2 software, which is the canonic pulsar timing software and has been already being used in the community for long. And also the Pine software, which has been developed in recent years, primarily by the NANOGrav community. For the single pulsar noise analysis, we're going to use the TempoNet software, which is a software toolkit built around the Tempo2 software, and also the Enterprise software, which is a standalone software that's been developed in recent years that can be used to do both single pulsar noise analysis and also search for correlated noise. So here is the layout of the entire IPTA DR3 work plan. So you can see that there are several steps involved. It's also mirrored in between these 2 pipelines. I just like to emphasize that the data combination of IPTA is not that straightforward. The primary reason is that each PTA are treating their data differently because of the different characteristics of the data. So the IPTA mission is really try to understand and incorporate all these differences. So this can sometimes go really into very technical details that can really increase your stress level very easily. Right, so because the IPTA DR3 including like over 100 pulsars, so to complete all of them, that will take a while. So that's why we decided to go in 2 steps. We will first deliver what we call the early DR3, which include 20 pulsars selected from the full DR3 list. And we selected the 20 pulsars for 2 purposes. First, we want to make sure the data set is sensitive for gravitational researches. So that's why we include the most precise PTA timers, as they can be marked out in black here, which are all covered by all of the PTA identities. And on top of that, we also don't want to just cherry pick the best ones. We also want to, make our life not very easy and challenge ourselves to make sure our analysis scheme is robust and is able to dealing with all of the corner cases and the challenging cases. That's why we also choose some pulsars which are known for a loud noise and potentially challenging for the data combination and the noise analysis. There's also marked in the red here. So yeah, so in total, the early DR3 will just both first give you a taste of the DR3 sensitivity for gravitational waves, and also building the fundamental layer and pathway for the full DR3. So I'm happy to say that after some work, we have we call the preliminary version 0 of EDR3 done. So this is some residual plots examples from the Tempo 2 pipeline. And here you can see timing data as a function of time, and see there's two different pulsars, 1744 and 1857. So you can, so the color markers represent a data point from different observing frequencies, and so you can see that they are sharing roughly same features before we do the noise modeling. And what is nice to see from the IPTA dataset is that you do have a really wide frequency coverage for most of the pulsars, going down to 300 megahertz up to 5 gigahertz. So this is an example produced from the Pine combination pipeline provided by Deborah Good. So here, differently, the different color markers represent the contributions from different PTAs. You can see that each PTA does start to observe the pulsar differently. So here, in the case of J1643, you start with the NANOGrav and the PPTA coverage, and then later on by the Meerkat and MPTA. So while in this case, in 2124, you start with the EPTA and PPTA coverage, and later joined by the NANOGrav, and later on by the Meerkat and the MPTA. So well, this is another
3 minutes left.
Yeah, this is another way of looking at IPTA data sets advantage. And so on top of data combination, we also run single pulsar noise analysis. This is also a heavily touched topic by this conference. So I'm just going to the basics. So what we consider in the single pulsar noise is white noise components and the red noise component. So white noise component, we consider a few factors, effect inqua, which produce the errors in TO uncertainty and additional noise to the data. And the red noise considered chromatic components and achromatic components. So the chromatic components, we have many contributions from the ISM, including DM variation, solar wind and scattering. Some of this already mentioned in Francesco's talk. And the achromatic noise components, including the spin of the pulsar, which are not correlated among different pulsars closely, and eventually the gravitational wave signal, which should be correlated among different pulsars. So if you're interested in the topic of PT analysis, feel free to check out all these talks. They are all excellent talks. Right, so I'm just gonna show you some results produced by the noise analysis of the EDR3. So this is some results from the TempoNet software. So here you have the posterior constraints on the red noise parameters and the DM noise parameters and solar wind amplitude. So here in this case, J1640, you have you can see that we have nice constraints on all these parameters. While in the case of J1603, you see that the DM, while the DM noise is well constrained, the other noise components are less. And so this is an example from the enterprise noise pipeline. So you can see very similar situations. In the 1744, you have well constrained noise, while in J1603, you don't. And it's effectively the same pulsar. So what you can do is just to do some size comparison by eye between these two pipelines. You can generally see that we have very good general consistency between the result of these two pipelines. So this is a very zero order comparison, and we are doing a more sophisticated comparison to make sure we have really high consistency in between these two pipelines. So this is a collection of all these noise analysis properties from our preliminary noise runs from enterprise. This is work done by Bjorn Larsen. And so here you can see the noise contours from DM noise, and this is the noise contour from achromatic noise. So you can see that all of the pulsars, we have well-constrained DM noise. While the achromatic noise is different from pulsar to pulsar, but it's also very interesting to see that for most of pulsars, they share very similar features in terms of achromatic ray noise. This is very promising because if we're anticipating that chromatic ray noise contribution are from the gravitational wave, you do want to see that they all share the similar features. So there's an alternative way of doing the noise analysis with the IPTA without combining the data. So I will refer to Paul Baker's talk on that topic. So finally, some perspective in the near future. So we have already version 0 EDR3 ready. So in the upcoming weeks, we will move on to the next phase to really fine tune towards the final version of it. What we want to do is optimizing our combination settings, noise modeling, and also going to do a lot of work on the pipeline comparisons. And of course, we will definitely be looking at the first gravitational wave searches with EDR3 very soon. So this is the work will be primarily done by the gravitational wave analysis working group. And of course, we will start the full DR3 combination soon. So in the upcoming months, we will complete the full analysis of the EDR3 that includes data, the noise, and the gravitational wave analysis. And of course, we will complete the full DR3 combination, which including over 100 pulsars, including noise analysis, and finally the gravitational wave searches with the full DR3. I cannot predict what we're going to have in the end, but it's definitely going to be more promising than this. So stay tuned for the IPTA. Thank you.
Thank you, Kuo. We have some time for questions. Please raise your hands. In the meantime, I can ask a quick question. What is the expected timeline? So you said there are two versions of the DR3, the one with 20 pulsars and one with all the pulsars. So what timeline do you guys have in mind?
So the completion of the EDR3 will be done roughly around the end of this year. And if you talk about the full DR3, that will be sometime next year.
Anjana has a question on the chat. Anjana, do you want to unmute yourself and ask the question?
Yeah, thanks. Thanks for the nice talk. I was wondering if you had to account for the the differences in the sensitivities of the different data sets coming from maybe longer time spans of some observations or different sensitivities of different telescopes by sort of normalizing over these, or how do you do that?
So the different sensitivities are already been reflected by the measurement error of the data, aka the time of arrivals from all those pulsar observations. So when you put them together, you do a least square weighted fit. So that's already been taken care of. And on top of that, so for each of the different data sets from different PTAs, we do completely separate noise modelings to capture the characteristics of the data set, just to make sure we model all the potential unmodeled noises in those data sets.
Great, thanks.
Any more questions? If not, we can move to Caitlin Witt.
Okay, so hello, I'm Caitlin Witt. Today I'm going to be talking about some work I've done with my collaborators, including our wonderful chair, Maria Charisi, as well as Stephen Taylor and Jessie Runnoe, on targeted gravitational wave searches for supermassive black hole binaries. So the general idea here is that even farther down the line from, completing IPTA DR3 and doing some more analyses on the gravitational wave background, we really want to get to a place where pulsar timing arrays can do multi-messenger astrophysics. So one of my favorite examples of how we can do this is in studies of supermassive black hole binaries, where we can look for them electromagnetically, and we can learn what the light that they emit has to say about them. And then we can also look for them with gravitational waves, because we think that these are one of the prime sources that pulsar timing arrays could detect as an individual source, so like a continuous gravitational wave signal. And by putting these together, the goal is to do multi-messenger astrophysics. And by doing that, we can do things like test GR and test all this modeling and make sure that we are confirming candidates that we think we might find in one or the other messenger. But until we get to this point, I sort of like to describe this as this Venn diagram that I showed and I've now broken apart. But until we actually make these detections, it's a little bit easier to think about this in separate steps. So we need to do some analyses on the electromagnetic side, we need to do some analyses on the gravitational wave side, and we need to do some analyses on the multi-messenger side where we put this together. But until it's a little bit easier to kind of think about this as more of a staged process rather than just seeing this all as one complete picture, especially before we've made a detection. So maybe I'll change this picture to first, especially in one of these targeted searches, we're going to actually look for one of these sources on the electromagnetic side. We're going to look for evidence of it in a light observing telescope. And then the focus of this talk is what we can do is use our gravitational wave analysis techniques to go target that individual gravitational wave from a specific candidate supermassive black hole binary. And that could tell us a little bit more about the system. It could give us some more hope of detecting it. And it might help us do some multi-messenger astrophysics as well. So the general idea here is there are quite a few ways to actually see a supermassive black hole binary electromagnetically. I'm just showing a few here just to give you an idea of the broad range of ways we can do this. We might see things like a post-merger galaxy. We might see things like a variable light curve that's indicating something like a periodic Doppler boost model from the motion of the supermassive black holes. We might see actual orbital motion on the sky of an AGN core, or we might see something in the spectrum or a dual AGN, although that would be a wider separation binary. But if we have one of these systems that we think could be an interesting candidate for a supermassive black hole binary, this actually tells us a lot about the system. At the very least, we would know where on the sky it is. And if it's in a galaxy, we would have a pretty good idea of the redshift. So we would know just about how far away it is. So these are already 2 or 3 parameters that would go into a gravitational wave search. We might also learn more things. For example, with that periodic Doppler boost model where we're looking for a periodic light curve, we might learn things like the gravitational wave frequency of the source, the chirp mass, or at least the total mass and the mass ratio of the binary, as well as maybe even the orbital inclination. So this is actually quite a bit that we can learn. And what this is really going to do is tell us, hello, look over here, do your gravitational wave search right over here on the sky. And that's going to help us do it a little bit faster and hopefully a little bit more efficiently. And we think this is a really excellent method because there are a lot of binaries already that exist for us to test. I like to show this plot on the right here from Cheng-Chung Zin's paper showing the candidates found in the Catalina real-time transient survey for periodic light curves. So these could be candidates for supermassive black hole binaries. And they're showing these against some predicted PTA sensitivity curves. And we can see that they lie in a very sensitive region of pulsar timing array parameter space. If we look over here to the left, this is the NANOGrav 12.5-year data set sensitivity curve to continuous gravitational waves, so the type of gravitational waves that these would emit. And we can see that they would lie right in this most sensitive part of parameter space. So this is a really nice overlap for us to look in. And there are already lots of candidates for us to go look at, even just from this one survey. And there are more out there. And there have been some studies on this already that have laid out the existing benefits. One is what I mentioned already, is that we have some parameters that are known, so they're a little bit more computationally efficient of a search. We have learned that that we will get a lower upper limit even if we are not detecting a gravitational wave, if we are doing this multi-messenger or targeted search over an all-sky search, as we can see from this plot here on the upper right. as we are gaining information from the multi-messenger search on gravitational wave frequency, so we move to the left on this plot, the upper limit on chirp mass goes down. So we're learning more information by working a little smarter. And then as we can see from this plot down here on the bottom left, we also have some better detection prospects as shown by Ting Liu et al. So as we gain more information on our binary, we get slightly elevated Bayes factors, which could help us move toward a detection in the future. However, I do really want to emphasize that continuous wave searches are still really complex. So I showed a few parameters that we will be able to already get an idea of from a targeted search, but there's quite a few more global parameters, namely the strain of the binary, polarization angle, gravitational wave phase. And the few that I want to highlight down here, the pulsar distance and the gravitational wave phase of the pulsar. And I'll tell you why those two parameters are important in the next few slides. Basically, all of these parameters are necessary to actually model the continuous gravitational wave in every single one of our pulsars. So over, for example, NANOGrav's 15-year data set, where we have 67 pulsars that are used for gravitational wave searches, that's a lot of parameters when we think about red noise and white noise as well. Those pulsar distances and pulsar phases are actually used to model what we call the pulsar term, as well as the Earth term of the signal. Basically, what's important to know is that the gravitational wave signal at the pulsar is not equal to the signal at Earth. As we can see from this animation I've made here, we get a sense for, okay, this pulsar is way over here, the Earth is way over here. Even though the Earth is in all of our baselines, that signal is not going to be the same. And it's the total distance between the Earth and the pulsar and that entire baseline that's what's going to be important to actually make our summed gravitational wave signal. So both of these signals appear in our pulsar timing array residuals. These signals can be related with geometry. So if we know where our pulsar is in space, we know where the Earth is in space, we get an idea of where our binary is in space, we can track back the orbital evolution of our binary and sort of get an idea of what the gravitational wave signal, both at the pulsar as well as the Earth, should be. But we need to know things like the pulsar distance and the pulsar phase to do that, hence all of these extra parameters. As we do this, we can then decompose this into the Earth term here on the top, as well as the pulsar term, which shows the lower frequency signal farther back in the binary's evolution, to get our full signal here on the bottom. However, some of these signals are a little bit more dominant than others. So one thing we really wanted to explore in this search is how can we actually simplify this? We know these targeted searches can speed us up and simplify these searches, but is there any way that they can help us do a little bit better and maybe cut out some of that pulsar term information? So our question was, if we target a candidate, can we just use the Earth term, at least as a first approximation, especially to start trying to make a detection, because that's going to be the strongest signal in there. So what we decided to do was simulate lots and lots of binary signals in a pulsar timing array data set, or in lots of different pulsar timing array data sets, and look for them all. So we searched with a targeted search pipeline where we're targeting a specific source on the sky, both with the full signal model and with just the Earth term only search. And then we compared them to see how we did. So the general thought is that, yeah, we could do this. So here I'm showing in one gravitational wave search from one PCA data set for both the Earth term only model, the orange contours, and the full signal model in blue for both gravitational wave frequency and chirp mass or total mass, which are two of the most important parameters for us to be looking at for one of these sources. And we can see with the correct values here in the dashed green line, these do more or less just as well. So this is great to see. This is really confidence inspiring. However, we can't just make some sweeping claims just based on one search on one binary. We need to actually test a lot of them. Nope. So that's what we did. I actually go forward in the slides. So we found this to be true over many, many tests. And by simulating thousands of binaries, we found that the Earth term only searches in this targeted pipeline recovered the continuous wave parameters to just about the same accuracy as full targeted searches. So if we're looking at this plot down here on the bottom, for each of our gravitational wave parameters that we searched over, for each binary, this is a histogram of many, many binary searches and the recovered median parameter, the posterior value, with the correct answers shown at the 0 mark. So we can see that these distributions of the recovered values are just about the same in each search. So we're really doing just as well for a lot faster in the Earth term only search. For an estimate of just how much faster the Earth term only search, what we did was we looked at the autocorrelation length of each of these searches and the posterior, the actual MCMC chains to get a sense of how efficient they were. Basically, the longer the autocorrelation length of each of these chains, the more samples we're going to have to run it for to get enough truly independent samples. And we can see for the Earth term only search, we on average have autocorrelation lengths of about 10 or stretching up to maybe 100. For the full signal model, these autocorrelation lengths are all very, very large in the thousands. So these chains need to run much, much longer and are much less efficient. We estimate over 100 times less efficient. So this is a really inspiring result that we think could help us out a lot in the next coming years.
Caitlin, 3 minutes.
Yeah, thank you. I'll stop going backwards. So the reason this is really inspiring is because we think there are a lot of candidates soon to come. So the Legacy Survey of Space and Time at the Vera Rubin Observatory is going to start in the next few years and will really be an unprecedented survey. And we think we'll uncover a lot of these periodic light curve candidates. So we'll have more to do and more to check. But the more efficient we can make these gravitational wave searches, the faster we're actually going to be able to evaluate them. And with all of the wonderful evidence for a gravitational wave background that has been released in the last few weeks that you heard some wonderful talks about yesterday and this morning, we are now starting to see Hellings and Downs correlations in pulsar timing array data sets. We're starting to see evidence of a gravitational wave background. For the purpose of this talk, what I'll just say is that we hope that this is a sign that we are, as pulsar timing arrays, starting to reach the sensitivities to start being able to detect other types of gravitational waves in the near future as well. So that includes continuous waves. So we will keep working diligently to make sure we're gaining sensitivity and working on these searches and modeling them as best we can for when we do reach that sensitivity. So the other thing we hope, as I love this figure shows that Maria made, is that the amplitude of the background that we are finding is quite on the strong end of all of the models that have been made. So what we're hoping this means is that if the gravitational wave background is made by binaries, it's really time to go find them because there could be a lot of them out there. And as we see from this other plot that Maria made that shows the wonderful overlap between these two different types of searches, we can see PTAs in the pink up here, as well as the periodic Doppler boosts down here in the blue. These parameter spaces overlap near perfectly. So this is really a great way to be looking for these if our goal is multi-messenger astrophysics. So the window to the nanohertz gravitational wave universe is starting to open, and in the next few years, we're going to have some wonderful opportunities for supermassive black hole binary science. And this multi-messenger universe is out there waiting for us. The low frequency gravitational wave searches are getting really exciting. Multi-messenger discoveries could come soon. And we have made some excellent strides in making more efficient targeted gravitational wave searches to actually learn about these supermassive black hole binaries. Thanks.
Thank you, Caitlin. There's already a question in the chat. Peter, do you want to go ahead and unmute yourself?
Oh, sure. Okay. Thanks, Caitlin. That was really cool. I just wanted to ask if you mentioned it, I missed it. You showed the parameter estimation comparison for the Earth term only search and the full signal model search. But if you have a weak signal in terms of having a detection statistics or detection confidence, do you get similar results for that too?
Yeah, that's a good question. This really just looked at the parameter estimation, and I think the important thing to know is that we did look at like sort of medium signal regime. So I think the cut was between like signal to noise, at least signal to noise of 5. So we were not looking for that initial like peak up of a detection statistic, but that is another good thing to look at.
All right, thanks.
Any other questions for Caitlin? You can raise your hands. If not, I can ask again one quick question. So Caitlin, oh, there is one in the Q&A, sorry. So Andrew, do you want to unmute yourself and ask the question?
Yeah, I can. So actually, this is the perfect slide to be on because this is the slide my question is about. Basically, I'm just looking at the parameter ranges here, and these are not what I would expect for PTAs. Is this just like an arbitrary scaling, or did you look at just some easy values and have plans to look at actual like, PTA parameter ranges?
This is basically like a % error. So it's like
Gotcha.
all rescaled to see like with the width of the posterior to see how far off it is.
Gotcha. Oh, I totally
Yeah.
missed that at the very bottom.
No worries, it's subtle, and I probably flipped the slide the wrong way and might have gone quickly. Don't worry.
Awesome.
Thank you for
so much.
checking.
Yeah.
Any other questions for Caitlin? Well, I can ask the one I had in mind before. So do you envision that the detection will be, we have an electromagnetic candidate and then we do a targeted search and we confirm that candidate, or we will have a continuous wave and then we will try to find the periodicity, let's say, in an AGN?
Hard for me to speculate. I hold the targeted searches really near and dear to my heart because it's so efficient and it can be more sensitive. But the other thing that is really important to balance is where these candidates actually are on the sky and where the PTA sensitivity is most sensitive. So lots of supermassive black hole binary candidates that are found electromagnetically happen to lie in NANOGrav's least sensitive area in the sky. When we have IPTA data sets, hopefully that sensitivity will even out a little bit. It might give us a little bit more chance of having an equal likelihood to find an actual candidate. But really, it just depends on what is out there in the universe and what's the loudest, and if it happens to be seen electromagnetically.
Thank you, Caitlin. Are there any more questions? If not, we can move on. There has been a slight change in plans, so Swiggum cannot give his talk, but Thankful Cromartie will give the talk instead. Thankful, if you are on, please go ahead and share your screen.
Okay, hopefully you can see me okay, maybe?
Yeah, we can see you, hear you, go on.
Perfect.
Perfect, thank you.
Okay, hi everyone. I did not know I was going to give this talk. Swiggum, who's been absolutely incredible in leading the NANOGrav 15-year data release, is unfortunately sick. So we are sad that he can't be with us, and I will do my best, but be nice to me. So let's go ahead and get started. You've already heard this a couple times now during the meeting. NANOGrav is the North American Nanohertz Observatory for Gravitational Waves. We have been doing this Pulsar Timing Array experiment since 2007. We're funded by NSF as a Physics Frontier Center, and we consist of a whole lot of institutions and a whole lot of people. It's far more than the 100 that I've listed on the slide here. We're very lucky to use some of the world's most kind of top-of-the-line radio telescopes, like the Green Bank Observatory in West Virginia, the Very Large Array in New Mexico, the Canadian Hydrogen Intensity Mapping Experiment in Canada, and the Arecibo telescope as well, while it was still operational. So you've already heard sort of the pulsar timing spiel. We'll talk about it in just a single slide. So pulsar timing is the process of creating a model, right, that can account for every single pulse from a pulsar. So there are a lot of different things that kind of change what time each pulse will arrive from a pulsar. These can be very basic things like the period of the pulsar, the period derivative, its position on the sky. If it's in a binary, then you have to account for its binary orbital motion. There are also effects, sort of more noise-like effects. Dispersion measure is a really big one that we've heard about already. There are effects from general relativity, especially in binary systems, and from gravitational waves. Astrometry is very important to account for as well. NANOGrav still accounts for dispersion measure variations using DMX, which is sort of this way of doing epoch-to-epoch measurements of the dispersion measure value. So you have some sort of small variation with time around a nominal dispersion measure value. We call these differences. So any difference between the actual time of arrival that we measure and the predicted time of arrival from the model, we call that a timing residual. And pulsar timing is extremely powerful. This is a very silly little animation about what pulsar timing sort of does, but it's the process of fitting this model, right, to some nominal pulse period. But pulsar timing is this extremely powerful sort of process that lets us time pulsars to precisions that rival atomic clocks. So this is this really phenomenal sort of method. We are, you can see in the plot in the bottom right, that, if you have a good model that's doing a pretty good job of predicting your times of arrival, you'll have these residuals that look kind of nicely scattered around zero without too much structure. But you can see that if you have something very serious missing from your model, here it's proper motion of 10 milliarc seconds a year, then you'll see this like sort of large structural change that's induced in the timing residuals and growing over time. So we're basically just trying to make the best models that we can for all of our pulsars that we time. Okay, so I mentioned all the telescopes that we're lucky enough to use. The loss of Arecibo definitely affected our collaboration very strongly. It was difficult, scientifically, personally, for Puerto Rico as a whole. So it was a very tough thing to deal with. In terms of our observing program, after we lost Arecibo, we lost about half of our sensitivity, right, to gravitational wave, to the gravitational wave background. And so we had to restructure. We now do monthly observations with the GBT, which was the case before, but we're timing almost 80 pulsars with the GBT. We get about 600 hours a year. For the vast majority of these, we only time them at L-band. We were really lucky in being able to start using the Canadian Hydrogen Intensity Mapping Experiment, which is CHIME, because that covers our sort of low frequency end of the spectrum. So 53 of our pulsars were able to not time with 820 megahertz at the GBT. Instead, we can use CHIME for that. And then we also use the VLA, the Very Large Array in New Mexico, for our high frequency timing. That's at S-band. And about 120 hours a year. So we have, we're very lucky to have this great observing program. We did have to drop a few pulsars after the loss of Arecibo, but the fact that we were able to regain so much of our sensitivity and sort of restructure in such a, convenient way, I guess, was very, very lucky. Okay, so the NANOGrav 12.5-year data set, this was published at the beginning of 2021. It had 47 millisecond pulsars, and it was the first time that we introduced a wideband data set. So this is just a different way of creating time of arrival measurements. You can read about it in these papers by Tim Panucci. He really sort of pioneered this method. It is really important, we don't have to go into the details, but the idea is basically that instead of taking a single TOA from each subband of your observation, right? So across the frequency band, you're going to take a single TOA and a measurement of the dispersion. And so this is a really fantastic way, both in this sort of era where we're using wider band measurements, but we want to reduce our data volume because we're timing more and more pulsars, because the computational requirements get a lot more sort of intense once the data set grows. And so the wideband timing helps us really shrink that data volume. For example, in the 12.5 year, it shrunk it by about 33 times. So this was a pretty impressive change. Okay, here's a little animation that sort of demonstrates the growth of the NANOGrav data set. Hopefully it works, yeah. So you can see that in the 5-year data set, we had 17 millisecond pulsars, but for the 9-year data set, which is the one that followed, we were able to add quite a few. And with each of these successive data sets, we're adding something like 3 years of data, though it varies obviously from data set to data set. And we've been, very lucky to be able to grow the observing program. And we know that this is very important, right? Just adding more and more pulsars to the array in terms of sensitivity to the gravitational wave background is the most important thing that we can do for our pulsar timing array in terms of sensitivity to gravitational waves. So this is what the 15-year data set looks like, which is sort of our most recently released data set. This is Agassiz et al. 2023, and you can see that we have quite a few more pulsars than we were working with in the 5-year data set. So this effort, as I already mentioned, was led by Joe Swiggum. He has done just, it's been an enormous amount of work over a really long time. So it's been a really, truly incredible effort. The data set includes 68 millisecond pulsars. We have both a wideband and a narrowband data set. The detection working group, the folks who are working on the gravitational wave background analysis and the other analyses that we've already heard about, are using only 67 of the millisecond pulsars because of the data span that they cover. We have slightly different requirements for what sort of constitutes inclusion of a pulsar in the data set versus in the GWB analysis. We do have both wideband and narrowband data, but there are some outstanding issues with wideband timing that we're still sort of trying to investigate. So the wideband data are not being used for any of the analyses except for some mass measurements that I'll talk about in a little bit. But those issues aren't affecting our background analysis or anything like that because those data are not being used for those analyses. We are using both new timing software and a new timing pipeline that we've developed. I'll talk about that in a second. The data set includes, it's called the 15-year data set, and it includes almost 16 years of data, but quite a lot of data on these 68 millisecond pulsars. It's also the first time we're including VLA data in the data set. So 0437 minus 4715 is one of those sort of most important sources for pulsar timing arrays. But it's quite far south. And so we have to use the VLA in order to reach that source. And so being able to incorporate VLA data on this source for the first time is really phenomenal for us. We decided to cut the data set off after Arecibo became non-operational in terms of the Arecibo data set. And then for the GBT part of the data set, we cut it off when one of the backends changed. Which is a pretty, it was just a natural sort of place to cut it. If you are interested, you can go find the data on Zenodo and on nanograv.org. That is accompanied by this pipeline that you're able to use in order to sort of take the data from start to finish through this whole process that we go through. So we're really aiming, and I'll move to the next slide, we're really aiming for sort of transparency and accessibility with this pipeline and with our data release. And so please do go check it out if that kind of thing is exciting to you. It's based on this PINT package, Pulsar timing package that Kuo actually already mentioned. So PINT has been under development for, I think, almost 10 years or something now. It stands for PINT is not tempo 3. So just saying that it's sort of a pulsar timing package that was developed independently of the canonical packages, tempo and tempo 2. And so this is actually a really great thing for pulsar timing array collaborations to be able to kind of cross-check results by having the independent packages. Why did we bother developing a pipeline? We really want to be able to time as many pulsars as we can, right? I already mentioned that the sensitivity increases linearly with the number of pulsars we're timing. And so we want in the future to be able to time like 200 millisecond pulsars. And that's just not going to be possible. I mean, it's barely possible with our 80, but we really needed to sort of streamline things and make things easier. We know that we're going to have to be reliant on sort of new techniques. Wideband timing is going to be very important when we enter the era of wider bandwidth receivers. And so these pipelines have to sort of account for all of these things. And as I already mentioned, we really wanted to have high transparency, accessibility to students. This is a really great way to get folks started on pulsar timing. And so go check it out if for whatever reason you are interested in these types of things. But I think it's a much nicer way of conducting these analyses, and we'll be able to sort of use this for future data sets, and that's going to make our lives a lot easier.
Thankful 3 minutes.
3 minutes? Okay, perfect. Thank you. So I'll just talk really quickly about a few of the different synergistic science analyses we did in addition to this data release. The first one, Jeff actually already covered last night my time, the sort of noise analyses really, really well. Basically, 23 of our pulsars have significant red noise. 10 of those measurements are newly significant, right? Because your sensitivity to red noise will grow as the data set grows in length. One of the pulsars no longer favors red noise, but basically things are as expected noise-wise. So I don't think there's too much to talk about here because you've already heard the advanced noise analysis, which is far more exciting. We also monitor changes in astrometric parameters very carefully. So only one parallax measurement changed by more than 3 sigma. There are 14 millisecond pulsars with changes in proper motion that were determined to be significant. All of the error bars on those measurements improved between the 12.5-year and 15-year data sets. NANOGrav chooses to always fit for proper motion and parallax, just to be conservative, even if it's not necessarily a very significant measurement of those parameters. Okay, really quickly, I'll say one of the really cool things we can do with the data set is sort of a census of mass measurements for our pulsars. So 50 of our 68 pulsars that are in the array right now, or in the data set, are in binaries. There's this phenomenon that happens in a very small subset where if the pulsar is going behind its companion along the line of sight and the plane is highly inclined, there is a GR effect called Shapiro delay, which is basically the companion delaying the pulses from the pulsar along the line of sight and causing a big spike in the timing residuals during superior conjunction. And so that lets us measure the mass of the pulsar and the mass of the companion. It helps us sort of break the degeneracy in the Keplerian mass function. And so it's a really fantastic way to precisely measure masses. And so we did have, you can see, this is gridding over the 2 parameters that we used to parameterize Shapiro delay. This is 1614, which was the sort of first 2 solar mass neutron star that was discovered by Demarest et al. In 2010. You can see that we have only very slight mass changes. The blue is the 12.5-year, the orange is the 15-year. The mass increased very slightly for 1614. This is in conjunction with an addition of significant red noise, which does affect the mass measurement slightly. So you can see, oh, this is no longer preliminary. I should have taken that off. But you can see that with time, we are able to really nail down masses with the NANOGrav data set, which is really fantastic. But there's still some which are either sort of maybe intriguingly massive, but extremely poorly constrained, or just obviously need more observations over orbital conjunction. And we're conducting campaigns outside of the NANOGrav observing program, or rather in addition to it, that will help us sort of nail down those neutron star masses much better. This is obviously important because if we measure the mass of very massive neutron stars, it helps us put constraints on the interior equation of state for neutron stars, which is really important and very poorly constrained. So I sped through that. I apologize. I'll say last thing here, just we do a lot of double checks. Here are some of our residual plots. You saw nicer versions of these yesterday. But we create split telescope data sets to make sure that the detection folks can sort of check for systematics in one data set or the other. That all came out okay, which was great. We check different timing packages and all kinds of things. So we really are being careful. That's all I want to sort of convince you of here. And we're looking towards the future. So we are very invested in the possibility of having this DSA 2000 project, which is a 2000 element interferometer. NANOGrav would have about 25% of all on-sky time if that project goes through. It would be really phenomenal. It would have Arecibo-like sensitivity. So this could be really great for us. We're also at the GBT, this ultra wideband receiver is undergoing commissioning, which is very exciting as well. It should improve our timing precision by something like a factor of 2. And so we're working right now with the folks at the GBT to sort of see how commissioning is going and to plan how our observing program is going to look in that new era at the GBT. So all of this very exciting stuff is going on. It's really fantastic. The other thing I'll mention, I didn't mention it because Kuo already covered sort of what's going on with the IPTA, but NANOGrav is really excited about the third data release for the IPTA. We've been working closely with everyone on this very difficult but very important project. And so we're really looking forward to that going forward as well. But I'll end there. Thank you so much, everyone.
Thank you, thankful. Any questions? We have time for maybe one question. You can raise your hands. Well, I can ask the quick question. You may have mentioned that and I missed it. What is the data volume and how much time does it take to process these data sets?
Yeah, so I think we have something like 1 million TOAs. It's quite a lot. Running all of our, the most sort of computationally intense part of it is the noise analysis that we run. That can take quite a while for pulsars where we have, almost 16 years of data. That's not all of our pulsars, though. A lot of these have only, or some of these have only been timed for, 5 or 6 years or something like that. So, noise analyses take, I don't know, on the order of like 6 to 12 hours for some of these. So that is sort of onerous. But we, you can really reduce the computational time by using the wideband TOAs. It's just way, way fewer data points. And so, for example, for the Shapiro delay mass measurements, when we do the gridding over the 2 Shapiro delay parameters, we're almost at the point where we have to use the wideband data set. It's just too computationally expensive not to. And so things really, we're reaching a point where we are really going to be sort of forced to embrace this wideband timing technique.
Okay, thank you. I think we need to move on to the last talk of the session, which is by Pat Meyers. Pat, please go ahead and share your screen.
Okay. Yeah, so thanks, Maria, for hosting this session. It's been really nice so far. So I'm going to talk today about stress testing pulsar timing array models. So my name is Pat Meyers. I'm a postdoc at Caltech, and this is work that I've done with Michele Vallisneri, Katerina Chatziioannou, and Alvin Chua. Okay. So pulsar timing arrays in one slide. So people have talked a lot about PTAs recently, but it's always worth going back over things briefly. So we treat pulsars as very precise clocks. So we can predict the arrival times of pulses from these pulsars to very high precision. Gravitational waves will cause slight deviations in the arrival of those pulses. And those deviations due to gravitational waves will be correlated between pulsars. So if you look at this plot down below, the correlation coefficient between pulsars is on the y-axis, and the angular separation on the sky between pulsars is on the x-axis. So if you have 2 different pulsars in the same direction, their correlation coefficient would be 0.5. If they're 90 degrees separated on the sky, they're actually going to be anti-correlated. And if they're separated by 180 degrees on the sky, then they're back to being correlated, but with a different correlation coefficient. And the amplitude of that correlation, like I said, depends on the separation of pulsars on the sky. And what we want to do is measure that correlation coefficient between lots of pairs of pulsars and get some measurement of this Hellings and Downs curve. And that's what NANOGrav and the EPTA and the PPTA have seen evidence for. So I'm going to talk today about sort of general posterior predictive checking. In this talk specifically, I'm going to talk about sort of a rapid post-processing step that allows us to test a few common pulsar timing array assumptions that we put into our models. But there are 2 papers on arXiv right now, and I've put their arXiv numbers there that go through quite a few different methods of model checking from this sort of posterior predictive checking standpoint. The first one does sort of Bayesian p-value interpretation of the typical pulsar timing array optimal statistic. And the second one incorporates what I'll discuss in these slides, plus some extra analyses that discuss leave one out pulsar tests and model checking from that standpoint, which is a little bit different than model checking in a typical sort of Bayes factor framework that people might be familiar with. So there's a lot that we've put out recently about model checking, and I'm going to talk about a small piece of that. But if people are interested, I would recommend looking at those papers. So it's worth discussing a few of the assumptions that we often make when doing our pulsar timing array analyses. So we typically assume that the power spectral density of the intrinsic red noise of pulsars follows a power law. So individual pulsars will have some fluctuations in their arrival times that's intrinsic to the pulsar, not due to gravitational waves. And the power spectral density of those fluctuations, we assume, follows a power law with a negative spectral index, meaning that low frequencies have a higher amplitude than higher frequencies. We typically assume that the power spectral density of the gravitational wave background follows a power law. And again, this is assumed to be a red process. So negative spectral index, higher amplitude at lower frequencies, lower amplitude at higher frequencies. We typically assume that the correlations between pulsars follow the Hellings and Downs curve that I mentioned on the previous slides. And these assumptions get encoded into our priors, which themselves have parameters that we may estimate. What I mean by that is we assume that the PSD of the intrinsic red noise, for example, is a power law, and so we will estimate the amplitude and the spectral index of that power law. So if we want to test some of these assumptions, the sort of classic way of doing this is to run a full-scale MCMC analysis that relaxes these assumptions sort of one after the other. But these can be costly, and if you want to test quite a few assumptions, then you have to do quite a few runs. But instead, what we're going to propose here is that we keep these power law priors, but after we estimate these power laws sort of spectral indices and amplitudes, we can go back and actually reconstruct the amplitude and phase of individual frequency bins and the correlations between pulsars. And we can then reevaluate the amplitude at individual frequency bins and do sort of a rapid reconstruction of correlations between pulsars. And we can get something that seems, that has an interpretation like a posterior on the amplitude in individual frequency bins that's subject to a prior that says that it should be a power law. So I want to discuss this in more detail because that's a pretty abstract statement. So one way of estimating the PSD is what we've got here. So people who work in, say, LIGO, for example, might be familiar with having some time domain representation of the data, taking a discrete Fourier transform and coming up with some frequency domain representation, and then taking that frequency domain representation and constructing a power spectral density with it. And in our case, that PSD might assume a power law or some correlation pattern. But in pulsar timing arrays, we don't have evenly sampled data, and the data isn't sampled at the same time for different pulsars. And so we can't necessarily take a simple discrete Fourier transform using sort of typical FFT algorithms. So instead, what we do is we start with some time domain representation, and we model that time domain data with a Fourier representation in sort of a Gaussian likelihood. And then what we do is we place Gaussian priors on the amplitude of those individual Fourier coefficients, and those amplitudes are subject to our assumptions like this PSD. And so in our case, for PTAs, each of these arrows represents a Gaussian likelihood assumption. And what that means is that we can actually do an analytic marginalization over that first step because Gaussians are easy to integrate over. And so we can actually jump from our time domain data to estimating the power spectral density, where we assume a power law and some correlation pattern. And so what you see down there, for example, is the amplitude and the spectral index for the common process from the 12.5-year analysis. And you can see the common process is consistent with that 13/3 spectral index and an amplitude of order 10 to the minus 14.5, 10 to the minus 15. And so this is what we get when we jump straight from the time domain data to estimating the PSD of the intrinsic red noise of every pulsar and our gravitational wave background. But once we have this PSD and we've assumed a power law and some correlation pattern, we can actually go back, because everything is Gaussian, we can actually go back and reconstruct that frequency domain representation. So we can take the time domain data and we can take this PSD that we've estimated, and we can estimate the amplitude of both, say, a sine and a cosine associated with each frequency, and you get out some amplitude and phase associated with each frequency that you might use to represent your data. But that thing on the right-hand side now, if we assume a power law in some correlation pattern, that power law will act like a prior, and the data will push us away from that prior. So individual frequency bins will have some prior due to this power law, but the data can push us away from that power law. And so this is what we're looking for, is in this post-processing step, is allowing the data to push us away from a typical power law. Or if we've assumed Hellings and Downs correlations, will allow the data to push us away from our Hellings and Downs curve. And this is quite useful because we can do this not just for the gravitational wave background, but for the intrinsic red noise as well for all of our pulsars. And this all comes out sort of in one final post-processing step. So I've got some simulated data examples here for you, and we're in the process of doing this on the 15-year data set. So as a first pass, we inject a sort of detectable power law gravitational wave background and realistic intrinsic red noise that's based on the NANOGrav 12.5-year data set. And we use a power law as a prior. So we run our typical MCMC in that sort of analytic marginalization regime to get the amplitude and the spectral index of our power law parameters on both the intrinsic red noise in every pulsar and the gravitational wave background. And then we do that final step where we reconstruct individual frequency bins, and we look at how well our assumption actually works. So in this case, we're testing the intrinsic red noise for a specific pulsar. This is pulsar B1937 plus 21. So the orange represent, so the x-axis here is frequency, and the y-axis represents some power spectral density estimate. The orange represents tracks that come that you would predict from our power law assumption. So we estimate the amplitude and the spectral index for the intrinsic red noise for this pulsar. We assume that that's a power law, and the orange represents sort of tracks that you might expect from that power law. The blue represents what happens if we reconstruct individual frequency bins, and we use those to construct a sort of quote unquote posterior on each frequency bin. And what you can see is that in general, the blue and the orange here agree, and that's what we expect because we injected red noise that had a power law. The orange here represents the injection that was made, and the black represents the maximum a posteriori for the intrinsic red noise that we estimated. So in this case, the blue and the orange agree with one another because we injected the model that we recovered with. But one could imagine that if intrinsic red noise for this pulsar didn't follow a power law, these blue would disagree from the orange. And we'll see an example of that in a moment. This is an example where, again, we've injected a gravitational wave background that follows a power law. And so the orange represents sort of expected tracks that you might get assuming a power law, and the blue represents what happens when we reconstruct individual frequency bins. The green is a data-only representation, so you can now think of the green as sort of being data-driven estimate of the spectrum. You can think of the blue as being a posterior, and you can think of the orange as being like a prior, basically. And again, you can see that the injected is a power law itself, that's the orange, and the black represents the maximum a posteriori estimate of this power law. So what we can see is that our power law assumption, which is encoded in something that's like a prior, is in orange, and that agrees with both the blue and the green in general. But what happens if we inject something that's not a power law, right? So in this case, let's look at the red curve. You can see that at low frequencies, this spectrum turns over. And so what we've done here is we've injected a spectrum that turns over at low frequencies and shouldn't have a detectable background at low frequencies. But if we assume a power law initially, when we estimate the power law amplitude and spectral index, you'll get something that looks like the orange, which is really fitting those middle three frequency bins. But at low frequencies, it'll extrapolate that thing up to higher values than what was injected. And so this represents some mismodeling. And this is something that, you might see if you ran a quote unquote free spectral analysis, which would be a separate run with a full MCMC chain. But with this sort of single post-processing step, we can get out some reconstruction of the individual frequency bins, because our prior might be a power law. But once we reconstruct individual frequency bins, including the data, we're going to get pushed down in those lower frequency bins. And so you can see the data only representation is there in green, and our sort of posterior is there in blue. And you can see that now the posterior is consistent with the injected value, whereas the orange wasn't. And the green as well, the data-driven statistic also agrees with what was injected. Okay, thanks. Yep. And you can see now what's nice is you can see sort of the push and pull between the data, the prior, and the posterior. So the prior is quite high, the data is quite low in that lowest frequency bin, and the posterior represents some middle ground between those two things. And this is what you expect in Bayesian statistics in general. But this is quite nice because we get out something like this at the same time that we get out the same sort of model checking on the intrinsic red noise for every individual pulsar as well. And we can also test our assumption of correlations. So if we put Hellings and Downs correlations into our model, then the orange represents the same thing. It represents sort of an expected set of realizations for the correlations that we can reconstruct. The green represents a data-only representation, and the green would be something that's sort of akin to what you would see in figure 1 of the NANOGrav 15-year analysis. And the blue represents this sort of reconstructed correlation pattern. And you can see that the blue has sort of wider error bars than the green, but it's still following the Hellings and Downs curve. But if we put in, say, for our initial model, no correlations, so we assumed no Hellings and Downs correlations in our original Bayesian analysis that goes straight from the time domain data to the PSD, then the orange here will be centered around 0. But the green, which is data-driven, will again follow something that looks roughly like the Hellings and Downs curve. And the blue is going to sort of have some interplay between these two things. And so you can see, again, the blue has wider error bars here, but the blue is, again, generally following the Hellings and Downs curve because that's what the data prefers. And so this is an example of what happens if you mismodel your correlations in your initial Bayesian step, but you do this reconstruction and you get back out the correlations that you originally injected. So that's all I've got for today. So we can evaluate many of our assumptions for pulsar timing array analyses in a simple post-processing step that takes, a few hours to run. But what we get out is an ability to test the red noise power law assumption for each pulsar, the gravitational wave power law assumption, and our correlation patterns, sort of all in this one nice post-processing step. And we can easily compare prior only, data only, and posterior estimates and look at sort of the interplay between these three pieces, which I think is quite nice as well. So at the bottom here, I've got, again, the archive numbers for these papers. And as I said, these papers also discuss, pulsar leave one out analyses, this Bayesian p-value interpretation of our optimal statistic. There's a lot there. I've only presented a small slice, and we're working on implementing these on the NANOGrav 15-year data set at this point. So I'll stop there and take questions.
Thank you, Pat. Any questions for Pat? So I can ask the first one again. Have you tried this in the recent PTA results, and what does it tell us for the assumptions that we make?
Yeah, so it's quite nice. So at the moment, what we like, I have sort of some preliminary results on the 15-year data, and what we see is that things are broadly consistent with a power law for the background. And the Hellings and Downs correlations, I mean, essentially it's the green and the blue here for the 15-year data set look quite similar to one another, basically. So there is maybe some slight deviations from the Hellings and Downs curve that we think are roughly consistent with what you would expect from noise. And I would encourage people to go look through that. There's a pretty lengthy discussion of that in the 15-year paper itself, sort of breaking down everything that's in the Hellings and Downs curve and in those correlations. But what we see is something that looks similar to Hellings and Downs and similar to a power law, which I think is nice. Yeah.
Thank you. Any other questions?
Yeah, hi. I'd like to ask something. Please correct me if I'm wrong. Could you go back to slide 12, please? So the current results that you have are more similar to this than when, from the simulations without the turnover in the frequency. Is that, right? Am I right? So this is how the results look like in the current data sets, more than what your simulations without the turnover, injection without the turnover showed.
Yeah, if you're asking about the 15-year data set, that is, the 15-year data set is broadly consistent with the power law. There's maybe some small, very small evidence for a turnover, some that's starting, but it's not statistically significant. So we don't see anything nearly as drastic as this, for example. If you sort of really parse what's in the spectrum in the 15-year analysis, it's not clear that there's a turnover. It could be that the second to last bin is maybe just a little bit higher than one would expect, and we really need a lot more data to, or maybe not even a lot, but we need more data to say whether we're actually seeing a turnover or anything like that. There's no statistical evidence for deviations from a power law at this point.
All right, thank you.
That were published in those papers or that I've seen. Yeah.
Okay, thanks.
But there's one more question on the chat by C1 Chen. Can you repeat how the data-only distributions are created?
Yeah, so this is a bit technical. So this is, these are sort of using what we've dubbed the single frequency optimal statistic. So what you get out when you do this sort of post-processing step is a realization of the gravitational wave background in every pulsar, and you need to combine those in some way to get some final estimate of this spectrum. And so we do that by doing something akin to the optimal statistic, so a noise-weighted average over that realization to get some estimate in each frequency bin, and you have some quote unquote model for your spectrum when you do that, and that model would be a delta function in each frequency bin. And this is sort of a crude way of doing this, and you can also do that on the real data. And this is sort of a crude way of doing this, and it can be biased in some cases. And you can see that especially at higher frequencies in some cases here. In a few of these plots. So actually, Kyle Gersbach, who's a PhD student at Vanderbilt, is working on understanding this single frequency optimal statistic better and sort of figuring out the biases and making sure that it's an unbiased estimator. But at the moment, we're using it to as a crude way of combining things to get a rough estimate, but it's definitely not a perfect statistic at the moment, and we're hoping to improve it moving forward.
Thanks, Pat, and many thanks to all the speakers of these sessions. This concludes the Pulsar Timing Array analysis session. Thanks to everyone for joining. I think we can get started. So welcome, everyone. It is my pleasure to introduce Jocelyn Reed, who will be the chair of the session. So Jocelyn, take it away.
Okay, welcome everybody to our session on nuclear and particle physics with gravitational waves. We'll just jump right in with our first speaker, who is Alex Jenkins, talking about gravitational wave event rates as a new probe of dark matter microphysics. So Alex, you have the floor.
Thank you so much, Jocelyn. Yeah, and thank you so much to the organizers for giving me a chance to speak today. I'd like to tell you a bit about some work which came out just about a year ago now, actually, but which has recently been accepted for publication in Physical Review D. This is work that was done with a great range of collaborators who really gave input on the different aspects of this problem. So we're tying together sort of particle physics, galaxy formation and evolution, and then gravitational wave astrophysics. So there's a lot of different steps, which I'm going to talk about here. But basically, the key result is what it says on the tin here with the title, that we think we can use the rates of gravitational wave signals, in particular stellar mass binary black holes that will be seen by next generation ground-based interferometers, as a new probe of the microphysics of dark matter. So the key kind of physical effect that we want to target here is the suppression of substructure in the clustering of dark matter in the universe. So one of the key kind of questions we could ask about dark matter, since we don't know what it's actually made of, is does it fit with the standard paradigm of cold dark matter? So in other words, are the dark matter particles collisionless? Do they only interact through gravitational force? So this is what I mean by non-interacting. And do they move non-relativistically? So are their velocities much, much less than the speed of light? So this is the kind of standard paradigm that we have, and it seems to describe observations on scales much larger than galaxies pretty well. But there's lots of kind of alternative models which would change what happens on smaller scales. So kind of from the size of galaxies down to smaller scales than that. So basically, if you change this paradigm, you allow dark matter particles to collide with other particles, or endow them with other interactions, or give them mildly relativistic velocities, all of those kinds of changes would change the way that dark matter clusters together on these smaller scales. So you can see these beautiful simulation images on the right-hand side here. These were not done by us. This is just taken from a paper by Markus R from a few years ago. So comparing simulations with identical initial conditions, but with different kind of dark matter models. And you can see that while the kind of large scale picture is the same, kind of regardless of whether you're looking at the dark matter itself or at the gas or the stars, if you zoom in and look at the smaller scales, you really start to see some differences. And in particular, the clustering is much less strong in models where the dark matter is not cold. So yeah, so as I said, there's many different models that go under different names, which all have this kind of similar phenomenology, this kind of washing out of structure on smaller scales. Throughout this work, we focus on the first bullet point here, just as a kind of example model. So this is interacting dark matter, so where dark matter can scatter elastically with neutrinos, okay? And this can give a similar kind of suppression effect on the small scale structure. But I want you to keep in mind throughout this talk that we think all of the main statements and conclusions that we make will hold for these kind of other scenarios as well. Okay, so gravitational waves, it turns out, are an excellent probe of this suppression effect at small scales. This is the key finding of the work that we did. So it's challenging to target this suppression with more kind of traditional astronomical tools, basically because the suppression is strongest, as I said, on small scales, which corresponds to the lightest dark matter halos or subhalos, and also at high redshift, because we know in our kind of standard picture of how structure formation proceeds that it happens in a bottom-up way. So you form the smallest structures first, and then those kind of clump together to form bigger and bigger structures over time. So you're interested in looking at very high redshift and very small scales, which is the kind of most challenging regime to probe, even with these amazing new instruments like James Webb. You would still miss these very small halos at high redshift. So it's hard to tell whether they're there or not, right? So hard to see whether there's some kind of modification to the dark matter scenario that is washing these structures out. So the key idea that we're proposing here, and we think we're the first people to propose this, is to use binary black hole mergers, and in particular, as I said at the top, stellar mass binary black holes like the ones you'd see with ground-based gravitational wave observatories, as tracers for these missing halos. right? So the idea is that even if you can't see these very light, very distant halos with light, with photons, you can see them with gravitational waves because they do give a significant contribution to the number of binary black holes in the universe. So if you break the cold dark matter paradigm, you have fewer light early halos and fewer high redshift binary black holes. So I'm sure many people listening to this talk already know this, but these third generation gravitational wave interferometers that are currently being planned and working towards being built will be an amazing tool to target these high redshift binary black holes. So in particular, we in this study, we were thinking about Einstein Telescope, which is a planned European observatory, and Cosmic Explorer, which is a planned US observatory. Combined, these will be able to detect essentially all binary black holes in the observable universe, which is kind of amazing. If you think we've gone from, in the space of a couple of decades, gone from detecting the very first gravitational wave signal to detecting basically all of the binary black holes in the universe. And in particular, if you think just about the ones coming from high redshift, so I picked this kind of arbitrary threshold of redshift of 7, you'll see later on in the later slides that that beyond that threshold is when you become very sensitive to the dark matter microphysics I was talking about. Above this redshift, we'll detect thousands of binary black holes per year, so we'll get really, really good statistics. So we kind of asked ourselves, can we use these very high number statistics to tell us something interesting about the dark matter? So the way that we do this is by creating a full end-to-end simulation pipeline, which is shown in this flowchart on the right-hand side here. So the idea is that you start with a parameter which describes your dark matter model. And part of the reason that we chose this dark matter model is it's described by just adding a single parameter to the kind of standard cosmological model, which is this U nu chi. So chi stands for dark matter, nu stands for neutrinos. And this parameter is proportional to the scattering cross-section between the two, and it's inversely proportional to the dark matter mass. And it turns out that all of the phenomenology of this model in terms of structure formation can be described with just this one dimensionless parameter, which is already constrained to be rather small. So from cosmic microwave background observations, we know it's less than about 10 to the minus 4. And recently this has been pushed down by another order of magnitude by looking at Lyman alpha forest observations. The main reason that there was that gain is that the Lyman alpha forest lets you look at smaller scales. So the idea is that here we're going to use gravitational waves to look at even smaller scales and make this number, constrain it to be even smaller, or possibly make a detection. So the idea is we start with this number, we use this as an input to a cosmological code called class, which generates the initial linear dark matter power spectrum. So it tells you how much the dark matter clusters together. And this is modified compared to the standard scenario. So as I was saying before, the amount of clustering on small scales is suppressed. So that translates into a suppression of the power spectrum on those small scales. So we generate a power spectrum in a given dark matter scenario. We then feed this into two different structure formation codes. So there's GalForm, which is a semi-analytical galaxy formation model. So this will take in the kind of initial dark matter density field, evolve that forwards in time, allow the dark matter to undergo nonlinear clustering due to gravitational collapse, and then track what the baryons are doing on top of that dark matter background. So what galaxies are forming and what are the astrophysical processes going on within those galaxies. So star formation and metallicities are the two kind of key things that we want to keep track of. We also use, so GalForm there is run just in what's called Monte Carlo mode. So we're not actually doing full n-body simulations, we're just tracking the kind of statistics of the galaxies and their properties. We also ran some full n-body simulations using a code called Gadget, but that was done without including the baryons. So just tracking what happens to the dark matter, how it clusters together. And so from this initial power spectrum, how many halos you form of different masses. That gives you what's called the halo mass function. And we did a cross-check between those two to check they're consistent, so that we have faith in the the key information that we want to get out of GalForm, essentially. And then the final step, this is where the gravitational waves come in, is we take this information from GalForm, so all of the galaxies in our simulated universe, all of the stars that are formed in those galaxies and the distribution of metallicities of those stars, And we feed this into a code called COMPASS, which is a binary population synthesis code. So essentially what this does is this simulates the evolution of individual stellar binaries over time. It takes into account all of the important processes in their evolution and how they eventually end up as stellar mass binary black holes, which can then interspiral and merge. So essentially this takes the structure formation information from Galform, and it gives us the merger rate of binary black holes as a function of redshift, so throughout cosmic history. And we repeat this for many different values of this parameter U. So we basically track how the merger rate history of binary black holes depends on the dark matter model. Okay, so before I even get to the gravitational waves, I just want to highlight that already with this method, just by looking at what happens with the galaxies, we can already beat the existing constraints. So this is already exciting, but what I'm going to show you on the next slide with the gravitational waves is even better. But just looking at the galaxies, we plot the galaxy luminosity function, so basically just how many galaxies are there in our simulated universe with different luminosities. And you can see that we cannot reproduce the observed data points here, these gray points, if this U parameter is larger than sort of 10 to the minus 6. So recall that that's already an order of magnitude lower than the existing upper limit from the Lyman alpha forest analyses. So already, just by looking at the galaxies that form, we see that you can already beat existing constraints. And this is really telling you that the way the galaxies form from the dark matter density field is already capturing some very relevant small scale information which might be missed by existing cosmological analyses. Okay. But now, this is a gravitational wave conference, so going to these gravitational wave observables, and in particular, the rate of binary black holes throughout the universe, this is where we can win another order of magnitude, it turns out. So based on our forecasts for next generation ground-based observatory network consisting of Einstein telescope and 2 cosmic explorers, we find that you can exclude 10 to the minus 7, so remember 100 times better than the best current constraint, at 95% confidence with just 1 year of observations, which we think is pretty exciting. So just how do you get that from this plot on the right-hand side? So these different curves that we're showing here are different merger rate functions as a function of redshift in these different dark matter models. So the black curve is for cold dark matter. You can see that that's globally the highest. And then as you start dialing up this neutrino dark matter interaction parameter, you can see that this curve gets suppressed more and more. And so at the 10 to the minus 7 level, you can see that this is a significant difference if you imagine populating these curves with many, many, many observed binary black holes. We also, as a kind of consistency check, we see that if you extrapolate these curves down to redshift 0, so the present day, that all of the different models we consider are consistent with this green band here, which is the local, present day merger rate inferred from the first 3 observing runs with LIGO Virgo Kagra. So this is reassuring that our models are consistent with the current state of the art of observations. Okay, so that's the headline result, and it's something we're quite excited about, as I said. The kind of key caveat with this method, of course, is astrophysical uncertainties. Other factors which could vary the rate of binary black holes you would see in the universe beyond just your dark matter model. And so I'll finish up with a couple of slides describing some analysis we did to basically reassure ourselves that these other astrophysical nuisance parameters are not degenerate with the dark matter effect that we're interested in. So just to show you, so what we did was we took 20 different data sets associated with this COMPASS code that I described before, taken from this nice paper by Floor Brookgarden et al. And these consider basically 20 different slight variations of the parameters that go into the COMPASS binary stellar evolution model. So they're labeled here with a bunch of different letters, and they change different aspects of the stellar evolution physics. So you can change the mass transfer, change the common envelope phase, change the way that supernovae function, change the stellar winds of the stars. And the top plot here is showing how this changes the formation rate of binary black holes. So there's a subtlety here in that there's a difference between the rate at which the binary black holes form and the rate at which they merge, which is what's shown in the bottom plot. And the difference between the two is basically the distribution of delay times between when the binary black hole forms and then how long you have to wait for it to in-spiral and eventually merge. So you can see if you look just at the, oh, sorry.
You're at your time. So
okay, I'll wrap up very quickly. Basically, we looked at the difference between those. We found that the dark matter effect is not degenerate, so we can still distinguish this 10 to the minus 7 even in the presence of these uncertainties. And so I'll wrap up and leave it there. Thanks very much.
Okay, thank you, Alex. We have our associated time for questions, so that thank you for the very quick wrap up. I realized sort of at the end I hadn't done any plan for alerting speakers to the end of the 15 minutes, so thank you for that. So we do have plenty of time for questions, though. Please go ahead and raise your hand if you have a question. While I wait for folks to navigate, though, I wanted to ask a little bit. You talked about this being applicable to the other dark matter models, which presumably have more than one parameter. Do you have an idea where this parameter is an effective mapping to those other types of effects too, or have you considered how that might work?
Yeah, that's a really great question, thanks. So with these other two models, we actually think that most of the relevant physics is also just captured in a single parameter. So for these kind of fuzzy dark matter models, where you have an axion-like particle playing the role of the dark matter, that would just be the axion mass. And also with the warm dark matter models, it's the mass of that particle which determines the way in which it thermalizes. So in terms of how you would map between these kind of single parameter extensions, that's something that Markus Mosbeck, who's one of the co-authors on this paper, is actively working on. He did find that a lot of the differences between these three models actually tend to, even though the linear power spectra, so the kind of the initial clustering, is quite different between them, you found that if you then process that through the kind of non-linear clustering of the dark matter, you end up with something that looks pretty similar between these three models. So that's the basis for this statement that we think our results are kind of applicable to all three.
Thank you.
Thanks for the question.
Yeah, any other questions from the audience? I guess since we did kind of cut off your last slide there, do you want to take a second just to quickly summarize that final plot that I didn't have quite a chance to look at?
Yeah, absolutely. Yeah, especially because, yeah, this is quite a dense plot, but basically you just want to look at the very top left corner here. So this is all the letters B through T are these different astrophysical models, and then IDM is this alternative dark matter model. And this plot is based on a Fisher analysis of, if I make all of these different changes, what's the covariance between them? So if I try to measure these 20 different parameters simultaneously, it turns out you can measure the parameter associated with the dark matter model to high enough precision that you can still constrain it with the data, the forecast data that we were talking about.
Very nice. Okay, I don't see anything else from the audience. So I guess, well, thank you very much, Alex. I really enjoyed your talk.
Thank you so much.
And let's take a minute then to swap over to, I think Peter is up next. And we'll give a minute to start on the time. So in case folks, we were discussing this before the session started, we swapped the order of the first and last speakers due to some time issues, but we'll continue now with our second speaker of this session on nuclear and particle physics with gravitational waves. Okay, so let's continue then. Our next talk this session is Constraining Neutron-Star Matter with Microscopic and Macroscopic Collisions from Peter Pang. So Peter, you have the floor.
Yeah, thank you very much. So as Jocelyn just said, I'm going to give a talk regarding constraining neutron-star equation of state with microscopic and macroscopic collisions. And in case you want to know more, you can also, and if you are not patient enough to go through the talk, you can just jump into this paper and see the details there as well. It's not working. Okay. So the big question of the day is like, what is neutron-star made of? And of course, no one knows the answer. Not even I know the answer, because if I know it, I will go to get my Nobel Prize. So it's a big question, and everyone wants to know the answer. But of course, as I said, it's a very big question, so it's very hard to answer. What about we ask a bit easier question? What is the radius of a neutron star? Now, if you ask this question to a bunch of nuclear physicists, the problem is not like you don't get any answer, like, oh, we don't know, or so on, but instead, you get too many answers. So like for here, in this figure, I plot is a figure taken from somewhere. It actually show like a bunch of equation of states on the so-called mass radius plane to see like with different equation of state models, what kind of mass radius relation is this predicting. And you can see that actually it's a very big mess. Like the curve is all around the place. There's no consistency between models. So everything will be basically model dependent, even the maximum mass and so on. And if you look into, let's say, a canonical neutron star, so like 1.4 solar mass, you will see a radius actually ranges from around 9 kilometers like to 15 or above kilometers, which is a very big range. So now the answer is like, which one is the correct one? Luckily, we are at the age of, often referred as like an observational science. So rather than just modeling a theoretical calculation, actually we can do a lot of observations. So for instance, here I'm plotting a bunch of so-called equation of states with pressure against their baryonic number density. And here we can see that actually different observation or different experiment actually can help us to constrain different part of the equation of state. So let's say if you go from the lower side, you see that for nuclear physics calculation or the nuclear physics experimental heavy ion collision experiment, they can roughly go to a relatively lower density, about 2 times the nuclear saturation density. But if you're going to look into like gravitational waves, in particular the in-spiral part, you can actually reach all the way around 4 point something, not as 5, but 4 NSAT. If you look a bit further into the most massive neutron star that observed by radio X-ray observations, for those because they are one of the most massive pulsars that we ever observed, we can actually push all the way to like 6 NSAT. But of course, for astrophysical phenomena, the highest one that we can see would be like at the moment the 2 neutron stars merge and they actually collapse in a black hole. So therefore, the electromagnetic signal from, let's say, kilonova, gamma ray bursts, or post-merger gravitational waves are the ones that we can push all the way to the almost very end of the equation of state that we can observe, at least inside neutron stars. So with all these information that I just mentioned, now we can actually construct some so-called, we refer to as a NMMA, Nuclear Multi-Messenger Astrophysics or Astronomy Framework, from which we can actually combine multiple channels of information together to get a measurement on the equation of state itself. So you can see from the upper left corner, you start with some nuclear theoretical calculation. In particular, this is the so-called chiral effective field theory, which is quite reliable up to 1.52 NSAT, but beyond which we have to do some more generic expansion. And this equation of state would be our so-called prior on the equation of state itself. And then on the next step, on panel B, we can now actually incorporate all these mass-only measurement on the pulsars. But of course, not only the pulsar, but also because we observed GW17, OX17, and there's evidence that actually the 2 neutron stars merge into a black hole at the end. And with the use of some quasi-inertial relation, actually you can also obtain an upper bound on the maximum mass supported by neutron star. So what you will end up with is like a purple band. Of course, it's not a hard cut, but like a Gaussian, but this purple band would give you a sense of what's going on here. And then the equation of state that predict the maximum mass beyond the purple band would be gone, or the equation of state predict the maximum mass below the purple band would be also gone. And then in the panel C now, we actually look into not just the mass, but also the radius measurement. Like for instance, the NICE observation, actually they are able to measure both the mass and the radius of this pulsar. And therefore we can incorporate this kind of information into our analysis. And in particular, you see that this bunch of equation of state here, which was still valid, but now they're basically all gone because of this radius measurement. All these are basically ruled out. And then, of course, in multi-messenger array, it's very hard to not talk about 170817, which is a very iconic multi-messenger event. From there, actually, we will incorporate it in two places. So the first one, of course, is the gravitational wave observation of it. And from there, we can actually have some also measurements on the radius of the two neutron stars. But then also, this event also is accompanied by the kilonova observation, so we can add some further information. And then at the end, we also like add 190425, but we all know that this event is relatively weak, so it's not super informative. But then what about terrestrial experiment? Because all we are talking about is like either theoretical calculation or astrophysical observation. Because like with this terrestrial experiment, actually we can look into the lower density a bit better than the astrophysical observations. So in order to actually incorporate that, actually this schematic chart actually summarizes it quite well, I would say. So first you can see that with the green side, we have the astrophysical observations. On the orange side, we have the nuclear experiment. And then they both meet up at the equation of state of a cold supernuclear matter. And then at the end, they will come all the way down to a joy constraint. And remember the color scheme, it will help a lot. So for instance, here, we can see that like, what if we include what kind of constraint, and then if they combine a different stage, what will happen? So similarly, like here is the prior with the chiral effective field theory. And now this green one actually is the final results that I just showed before for all these astrophysical observations. So you can see this undoubtedly a very strong information incorporated in this process, because you see how the mass radius band changes from this all the way to this. And you can see the 1.4 solar mass neutron star is relatively well constrained now. But if you look into the heavy ion collision, then you may say, oh, this seems very just like the prior itself, right? It does not change much. And even if we combine it with the astrophysical observation, this blue band is very similar to the green band. If you look into a bit more detail, like let's say the radius of a 1.4 solar mass neutron star or a radius of a 2 solar mass neutron star, you can see the final blue joint constraint actually is very similar to the green constraint from astrophysical only. So you may say, adding heavy ion does not help much, right? The reason why it seems to help much is because we're looking into a too high density. If you look into the microscopic equation of state, now we are seeing something very interesting. So actually, before going to all this band, I would want you to look into the upper right corner, the panel E. Now you can see that actually both the orange, therefore the result from heavy ion collision, and the green one from the astrophysical observation are both deviate quite significantly from the prior itself. Not only that, you can see that the orange actually defines how stiff the equation of state should be, and how consistent is the heavy ion collision with the astrophysical observation, which is something novel, I would say, because we never know. We're from vastly different channel, vastly different modeling, but still we end up with the same thing. And then here you can see that like this orange band tells us like the equation of state should be a bit stiffer than what we think from the astrophysical side. But of course, again, if we go to 2.5 ansat, a bit higher, then this information start to be dilute, mostly because you see the heavy ion collision data actually only gives a band, this purple band, roughly at the lower density. With high density is basically everywhere. So at the end, we have this plot. You can see that from different observation, from the current effective field theory, including the maximum mass, including the nicer observation, and so on and so forth, from gravitational waves, kilonova, and then at the end, heavy ion collision. Now we can see that like how these constraint on the pressure or the constraint on the 1.4 solar radius of a 1.4 solar mass neutron star actually converge down to a much smaller interval. So still the big question, what's neutron star made of? We still don't know. Then what's the radius of a neutron star? Now we have a bit better answer. Instead of from 9 to 15 kilometers, we will say it's 12 kilometers plus or minus 800 meters roughly. So that's it for my talk. So feel free to ask any question if you want.
Thank you very much. And that was, I think we have plenty of time for questions. So give folks on the chat a bit of time to raise your hands. As well, we're waiting. So as you fold in all these different astrophysical and terrestrial observations, do you see any tension in between different observations? I know I know there's, I haven't heard that there's anything statistically significant, but is there anything you notice as maybe two constraints pulling in different directions?
So as you just said, actually there's not statistically robust tension yet, mostly because our measurement itself is not super accurate. But one thing I would like to note is pulling different direction actually is observed within the astrophysical side. So actually for gravitational waves, actually we know that it actually putting an upper bound on the stiffness of the equation of state. Therefore, it allows for soft equation of state as soft as they want, but they cannot be too stiff. And for kilonova, actually it's the other way around. It allows for stiffer equation of state. So that's why they combine and they have a good constraint. But what's surprising is that when we try to combine the nicer observation, in particular, the nicer of J0740, so therefore the more massive one, we actually see that actually it's trying to push to a direction even stiffer than what AT2070 GFO is predicting. So it's like it's very small tension, but actually it's very small, as I said. It's just a bit stiffer than what we thought, than what we thought, but still no strong tension so far.
Thank you. Okay, we have a hand up from Suprovo.
Hi, can you hear me?
Yeah.
Okay, so hi Peter, so thanks for the great talk. So I wanted to ask one question, like how robust are these heavy ion collision experimental results? Like you were mentioning, do they come at the same footing as chiral effective field theory or astrophysical observation, or do they have some model dependence in these results also?
Yeah, so actually in this, let me go down to this panel. So basically the main question is how do we get this purple band? And of course, this purple band actually is a combination of multiple heavy ion collision experiment. And of course, there is modeling involved. So one might, as you suggest, it could be model dependent. But luckily in our paper, actually what we did is actually we basically vary almost every aspect that you can do on the heavy ion collision data side. Like what if we use a completely different equation of state functional? What if we actually relax some kind of measurement or some results of the heavy of the nuclear physics parameters and so on? But at the end of the day, after we vary all this, actually our result is still robust and actually still very consistent, even with all these vastly different modeling also. So undoubtedly, there is a very slight model dependent, but I would say the conclusion that we are seeing here actually is model independent enough, I would say, and robust enough.
Thanks. So can I ask one more question? If there is...
Yeah, we have time.
So if you go to the 7th slide, yeah, it's a bit technical, but yeah. So there it is, I think it was showing SNM, right? Symmetric nuclear matter.
Yeah.
So, but neutron matter is generally asymmetric nuclear matter. So how do you compare in the same footing?
Yeah, so actually what we did is like the first there's a symmetric part, but then to promote to neutron star, actually we need to also use the so-called RCEOS experiment result, which actually measure the asymmetric part of the, what's it called? The gamma RC, so the asymmetric power in exponential. And then from there, we can actually push the symmetric measurement to the neutron star equation of states.
Okay, thanks.
Okay. If we don't have any other hands, I'll take the last maybe minute here to ask, what is there any future nuclear physics experiment or terrestrial or astrophysical observation that you think would be most impactful given what we know so far?
So the most impactful, or like the big wish, of course, is to look into Alice, because they're actually proving very high temperature and so on. But of course, to actually get this information, we need not only data analysis advancement, but also theoretical, because you need tons of transport model to push it back to what we want. But I would say that would be the holy grail. Actually, if we get anything from that side, it will be extremely exciting, because they're proving a much higher temperature, and actually those parts will be very different. And that would be the ultimate goal. But for astrophysical, of course, if we get more, because after all, we only have one multi-messenger observation at all. If we get another one, it could already change a lot, because even just one we can do a lot of science. If we get two, if we get three in O4, then the astrophysical side will be much tighter, and then the heavy eye has to catch up. So
let's hope.
Yeah, fingers crossed. Let's hope we get more.
Okay. Let's then take thank you again, Peter, and thank you from everyone. Now, I guess we have a couple minutes before our final speaker, which, because of the schedule swap earlier, will be Bikram. So I'll give folks a minute to grab water or whatever. And Bikram, if you want to get your slides set up to share, then I'll introduce you when we hit the scheduled time. Okay, so we're at the time for our next talk to start. So our final talk this session will be Bikram Keshari Pradhan will talk to us about constraining nuclear parameters and neutron-star equation of state through F modes from glitching pulsars. So Bikram, you have the floor.
Yeah, thank you for the introduction, and thank you to organizers for the opportunity. I am Bikram Pradhan, working a PhD student at IUCA with Professor Debarati Chatterjee. Yeah, so I just the work I am going to present is like done in collaboration with Dhruv Pathak, a postdoctoral student at IUCA. I just quoted the ePrint link here. Yeah, so we have like already witnessed in previous talk different like the importance of the neutron star. Just to recap, so the neutron stars are basically very interesting in different aspects of fundamental physics and understanding the behavior, and one of them being the extreme matter that is present inside the neutron star. And though we have a little bit understanding regarding the crust or like the little bit towards the outer core, the core still remains the uncertain, and we generally don't know what they're made up of or like how the matter behaves at that point of the density. So for that, one have to rely on the physical motivations, and depending upon physical motivation for cold neutron stars, you will get a pressure or density relationship that more commonly known as the equations of state, and which plays a vital role in finding the neutron star observables. For example, if you solve the hydrostatic equations, you will get the neutron star configurations, and different astrophysical observations like coming from the electromagnetic telescopes, like the mass radius measurements or like the maximum mass measurement, they can help constraining your model. And they can also be the source of the gravitational-wave and binary. And the deformation in the tidal field depends upon what the equation of neutron stars are made of, basically in the equation of state. So this deformation basically can be measurable in terms of the tidal deformability, and that have been widely used to constrain the neutron star equation of state that we have already witnessed from previous talk. So in addition to this binary system or like the electromagnetic radiations, These informations are mostly for the binary stars, and also we don't have much information regarding the isolated case. In addition to this binary systems, the Neutron-Star can also have the gravitational modes in case of isolated stars, like due to their different oscillations. And this idea is somehow similar to the seismology, or mostly commonly used in the solar physics. The term is helioseismology, where you detect the perturbations or you measure the perturbation properties and try to infer the stellar properties like the interior or the macroscopic properties. And in case of Neutron-Star, the oscillation modes are mostly classified depending upon what the restoring force, like you can have a pressure mode, a pressure as the restoring force of the buoyancy, gravity mode. Or the fundamental modes are also there, like also shows be more relevant, and that get excited in different astrophysical events, which is mostly frequency range in 1 to 3 kilohertz. And I'll mostly focus on the fundamental part, as the teacher suggests these are mostly more likely to be excited in different events. These mode parameters like the frequency or the mode damping time, that depends upon the equation of state. So the detection can then be used to constrain the Neutron-Star equation of state, or to tell something about the Neutron-Star interior. And this proper like this is the mode excitation maybe can happen also in the binary, the isolated case. And the isolated case, this will be more helpful, like as we may not have many other observations telling about the Neutron-Star interior. Yeah. So the astroseismology problem was proposed initially in the Anderson recorders. The idea is basically, if you are worried about the Neutron-Star macroscopic properties, so there are basically universal relations, like you express the more properties in terms of the macroscopic properties such as the mass, radius, or like you can also use the moment of inertia and other parameters as well. And if you detect somehow, let's say detect this parameter, you measure like this imaginary, is basically the damping time and the frequency, then you can tell it something about the mass and radius. So to demonstrate this or you can inversely use this. You can directly use like the way you have used to find the equation of state using the mass radius. You can use the observation of frequency and damping time to constant your equation of state as well. To demonstrate this inverse problem, that like the constant equation of state, we have adapted this methodology from Runnoe et al. So the assumption is basically the F-mode is being excited in the glitching pulsars, and the excitation is up to a level so that the gravitational energy is equivalent to the glitch energy. And the gravitational wave is modeled as a damped sinusoid, with the F-mode frequency, like the damping time is also order of 100 to 500 millisecond. To find the possible candidate, we do the following. We consider all the glitching pulses from the Jodl-Blank glitch catalog, and we assign the relative change in spin frequency that available in the glitch catalog. But the other properties like the spin and the distance, everything we assign from the 18M pulsar catalog. Now the unknown quantities like the moment of inertia of real or the frequency of the mode and the damping time. For that, we assume an equation of state and randomly assign a pulsar, these pulsars to masses randomly. And we associate all these properties to the pulsars, like all these pulsars from corresponding equation. Like you assign the masses and the corresponding properties you assign from the equation state. This is the same methodology what have been done in like and doing that we calculate like how what is the typical SNR we expect in different configuration. We mostly take the A plus, like A plus is basically H1 and L1. H1 like the LIGO detectors and the Voyager detectors advanced sensitivity, and the LIGO detectors are basically working at 0.5 sensitivity and 80. And if you take a SNR cutoff of nearly 8, you will find like in A plus also only this particular line you are looking at is basically correspond to Vela only. So the Vela glitches may be detected like the F-modes from Vela. But in ET, you can have also you may have it written from other pulsars. So once you detect discuss the potential candidate, so to go to the Neutron-Star equation state, we like first find out the posterior of the frequency and damping time, like what we have the model parameters here, the frequency and damping time. Then we translate in a way to the equation state, which will come later. So to find this posterior of the frequency and damping time, So like as already mentioned, like for the potential sources, we consider these priors I have just quoted here, like the frequency, for the frequency and the damping time, and we perform this parameter estimation in BLV, which is a Python like package for the GW inference, and we fix the distance and other scribe positions as we are mostly targeted to the targeted pulses. We know the positions of the glitching pulses, and also one thing we have not considered the spin correction to the mode parameters as well, and also ignore the high spinning pulses. For example, if you look at the corrections, like the first leading edge correction is will be basically the omega is the spin frequency and the Kepler frequency, and we only take the pulses which are below 100 hertz. It's basically like most of them are nearly 50 hertz as well. So and the Kepler frequency goes as order of like kilohertz, like 1000 hertz. So the correction will be up to 3% in the mode parameters. So if you do the parameter estimation, what we found is like the frequency get precisely determined, and whereas the damping time can have a significant error, and the error can go up to 20 to 50% in A plus, depending upon what scenario, like what model, like other parameter model you are considering. And in ET, the error is less as expected due to the increasing sensitivity. So these uncertainties are like in agreement what was proposed 2 decades ago by Cocotte et al. During a Fisher matrix analysis. So now once we have this posterior of the F tau, so what one can do, like earlier as I have shown the universal lesson, you can use the universal lessons for your favorite pair. Then you can find this properties of the Neutron-Star, and then like the price law you do for the MR or the M lambda posterior, you can use to try to constrain the Neutron-Star equation. Other thing you can do, use the frequency and damping time posterior. You don't assume any universal relationship. Like you solve like for the F1, like the mass area, you can solve for the more parameters and try to constrain the Neutron-Star equation. But the problem with this method is you cannot always like solve for the F1 damping. Like, you can always solve, but that is very computationally expensive, and you may not be able to implement in aviation formalization. This maybe you can do if you have the tables in your hand, but it's generally not preferable because the solving for this frequency and damping time takes a lot of time, and it's computationally also not preferable. And the other thing, you can assume your US model. You can solve basically for the MR or M lambda, and you can use the universal relations to go to equation. There are a few work I have quoted in the slide. So like, for example, if you suppose find F tau and you want to find out the M and R, even assume equation of state and find which region of the mass radius explains your F tau. But in that case, that will be highly biased, and you can see more detail in this paper. I have just cited here. So that will be highly biased because the equation set you don't know, and depending upon different equation set, you will get a different mass radius. And also there's one work like you can find like they try to consider the equation set with polytropic description of the matter, but considering rotation as well. So what we follow is basically we try to consider the Neutron-Star equation set, at the same time we try to constrain the nuclear parameters in our work. And we basically followed this method. We just solve the M lambda and try to implement the universalism. So to give the model idea, so we worked with the relativistic mean field model. Just to give a introduction to the model like the variance are like integrated through the Mason axis, and basically in the mean field you see the measures are in the mean path, and this measure coupling constant, this G sigma, G omega, or this 0. So they are calibrated basically towards the what model, like what nuclear uncertainty we have, nuclear parameters we have in our hand at the saturation. So depend like the parameters are basically saturation density, the binding energy, and the effective mass or the compressibility. And especially if you look at this 0, which is basically for the isospin asymmetry. These parameters are mostly like calibrated with symmetry, energy, and slope. So just in the roughly, if you have these parameters, you can generate like the equation state from within this model. Then to implement find the posterior like the equation of state, we did in the basic formalism, and the posterior probability for the equation of state can be written in this way. It's with file with the prior. So this likelihood function, we calculated a little bit simplified to save the computational cost, and by marginalizing over the mass for this parameter. And the probability of this probability quantity, we take what we have already obtained from Bilby. Like from Bilby, we have the posterior of the f for given event, and we just like equivalently divide the prior to get the this probability function. And here we just like once you decide the mass, the f and tau are just calculated using the universal distance. So we're not solving for f and tau. For the prior properties, we just take the prior sort of like inspiring from this particular the Morgan. So we we take the truncated Gaussian and we fix the prior at basically injected value, just the sigmas and the tangential limits that we taken from this Morgan paper. And now with this methodology, if we go and see the what is the bias in the nuclear parameter, what is the uncertainty, we consider first one event with Vela, and we try to reproduce the nuclear parameter. So if you see in a like 90% within calibration interval, we found that nuclear effective mass get better constant. Like it can be get constant within 10% in A plus or maybe 5% in the 80. And the among other parameters, the slope of symmetry gets slightly constant, but we don't see much other constant like constant on the other parameters for a single event. And the better constant, the nuclear effective mass is quite expected. Like for this model in our earlier work, or we have shown that this M star shows strong correlation with the frequency and the damping time of the neutron stars actually. So this is what we have gotten for this single event. Now we use this posterior to reconstruct the neutron star equation of state. Like this, the energy pressure or even the orbital uncertainty in the mass radius, and the other properties like the sound speed and the pressure as a function of density. And also we try to constant like try to see how well the properties of other properties of the neutron star can be constant from this posterior actually. So what we found is basically the frequency of a 1.4 solar mass star can be constant within 100 hertz in A plus, and it can be constant within 70 hertz in 80. And all of these I am saying within a 90% radial interval. And the radius like also can be get better constant. So now, as I previously shown, like there could be multiple events like in A plus from Vela or maybe in 80 with different pulsars. So we consider multiple event scenario as well. So we take first 10 events from Vela in A plus and the same 10 events in 80. And then for another case we consider 10 events, but we don't consider Vela. So that this is basically in Einstein telescope, we have only other pulsars, don't consider the Vela. So what we found posterior is like, well, the nuclear parameters get better and better constant, and the nuclear effective mass get highly constant with the 80 if you include only Vela. And what we found the posterior of the nuclear effective mass within this model within 10 Vela excluding Vela is somehow similar to that of what we have gotten in A plus with including Vela only, with considering Vela.
You're at the time to wrap up in the next minute or two.
Yeah, okay. Okay, so this is, and then similarly we can still like try to recover the posteriors of the equation of state, and you can see the improvement in the posteriors. And now the frequency can get constant within 20 hertz in 80 or within 30-40 hertz with in A plus, like the frequency of 1.4. Then we try to combine this one event of the F mode with the existing astrophysical measurements like the mass and uniformity from the 70 to 17, and the mass radius measurement from the pulsars, like from these pulsars basically. And there's a bias you can see in the corner plot, and we see mostly like the effective mass get better and better constant. We don't see any bias in other parameters. And if you translate to the equation of state of the MR, you can see how the posterior gets like things like basically you get better and better measurements if you combine the F mode observations. And I just summarize the findings here. Before concluding, I just want to say the method we use is basically a particular RF model. We have not also included the rotation. These things need to be implemented properly. Again, the universalization we have shown while doing the Bayesian may not be valid when you consider other configurations like the hybrid twin stars or quark stars. Yeah, so these are my findings. Thank you for the attention.
Okay, thank you very much. We have time for maybe one question. If there isn't one from the audience, I had a quick question. When you're calculating the time scale, do you assume, is that just from all the energy going into the gravitational mode and radiating?
Yes, that's the assumption. Yeah. So all this, yes, this assumption we get.
Okay. And then I guess the other quick question I had is, it surprised me a little bit that the improvement with Einstein telescope over advanced LIGO was sort of a factor of it was not an order of magnitude, I guess. Do you have any understanding what limits the improvement as the detector sensitivity increases?
Yeah, actually, I didn't get. So asking about this plot, like these uncertainties.
Yeah.
Yes. Actually, I don't. Maybe can we repeat the question? I don't get exactly.
Okay. I mean, maybe I just haven't looked at this particular observation.
Actually, yeah. So maybe if you can look at this error, this work I have studied. So there is an expression for these errors in terms of the SNR. Actually, I don't remember exactly how it goes, but yeah. So it depends. Yeah, in the experimentation there is a direct relation in terms of the more parameters on the SNR of the detector.